Something is wrong with the universe. Not metaphorically wrong, not philosophically wrong, measurably, numerically, reproducibly wrong, in a way that has caused the world's finest cosmologists to stop mid-sentence, stare at their data, and quietly wonder whether everything they thought they knew about space, time, and the structure of existence was built on a foundation that is now crumbling beneath them. Two groups of scientists measured the same thing. They used different instruments, different stars, different methods, different continents. They checked their work, they checked each other's work, they ran the numbers again, and they got different answers. Answers that should not be different. Answers that cannot both be right. Answers separated by a gap so precise and so persistent that the odds of it being a coincidence now sit at roughly 1 in 50,000. The universe is expanding. We have known that for a century. But how fast it is expanding depends, apparently, on who is asking. And that is a problem that reaches far beyond astronomy. To understand why the universe's expansion has become the most contentious measurement in all of science, we first need to understand what expansion actually means. This is not a trivial thing to grasp, because the word expansion carries with it a set of wrong intuitions that most of us carry around without ever being corrected. When most people hear that the universe is expanding, they imagine something like a balloon being inflated, galaxies rushing outward through empty space the way shrapnel flies outward from an explosion. This picture is wrong in a way that matters enormously. Galaxies are not rushing through space. Space itself is stretching. The fabric of the cosmos, the medium through which light travels, the geometry within which atoms vibrate, is growing. Galaxies are not moving away from each other because they are moving. They are moving away from each other because the distance between them, the space they sit in, is increasing. This is not a word game. It has physical consequences that have taken physicists a century to fully absorb. The clearest way to feel the difference is this. Nothing can travel through space faster than the speed of light, roughly 299,792 kilometers per second. But there is no speed limit on the expansion of space itself. There are galaxies at the edge of the observable universe whose light will never reach us, not because the light isn't travelling toward us, but because the space between us and those galaxies is expanding faster than light can cross it. We live in a universe that is in places expanding faster than light, and that is not a violation of any law of physics, because no object is moving faster than light through space. Space itself is what's moving. This distinction, the difference between movement through space and the expansion of space, sits at the heart of everything that follows. The expansion of the universe is described by a single number. It is called the Hubble Constant, denoted h0, where the subscript 0 means right now, today, at this moment in cosmic history. The Hubble Constant tells you how fast space is expanding per unit distance. It is measured in kilometers per second per megaparsec, where 1 megaparsec equals approximately 3.26 million light-years, or 30.857 quadrillion kilometers. What the number says in plain language is this: for every megaparsec of distance between 2 points in the universe, those points are moving apart at a speed equal to h0 kilometers per second. A galaxy that is 1 megaparsec away is receding from us at h0 kilometers per second. A galaxy 2 megaparsecs away is receding at twice that, 3 megaparsecs 3 times. The relationship is linear and it holds everywhere, because it is not movement, it is geometry. The expansion is uniform, woven into the fabric of space equally at every point. This proportionality was the discovery that made Edwin Hubble famous, though the theoretical groundwork for it had been laid 2 years earlier by a Belgian priest and physicist named Georges Lemaitre, a man who derived the expansion of the universe from Einstein's own equations before anyone had observed it directly. Lemaitre's original 1927 paper in a Belgian scientific journal went largely unread by the broader scientific community. Einstein himself encountered Lemaitre at a conference in Brussels that same year and, according to the account of Lemaitre himself, told him, "Your calculations are correct, but your physics is abominable." Einstein at that point still believed the universe was static. He had even modified his own equations, inserted a mathematical term he called the cosmological constant, specifically to prevent them from predicting an expanding universe. He could not stomach the idea. Then, in 1929, Edwin Hubble published his observational evidence. Using the 100-inch Hooker telescope at Mount Wilson Observatory in California, at that time the most powerful telescope in the world, Hubble had measured the distances to a number of nearby galaxies by identifying a particular class of pulsating star called a Cepheid variable. Cepheid variables are extraordinary objects. They breathe, they expand and contract over a period of days to weeks, and the period of that pulsation is precisely linked to the star's intrinsic luminosity. Longer period means brighter star. This relationship, discovered in 1908 by the astronomer Henrietta Swan Leavitt, while she was working as a computer at Harvard Observatory, a role that paid less than clerical work and was considered beneath the male astronomers who would later take credit for its implications, is the foundation of all cosmic distance measurement. Because if you know how bright a Cepheid truly is, and you can measure how bright it appears from Earth, the inverse square law tells you exactly how far away it is. Distance measured in starlight. Hubble used this technique to establish that the galaxies he was studying were not merely clouds within the Milky Way. They were island universes separated from us by distances too vast for the human imagination to comfortably hold. And when he plotted their distances against their recession velocities, the speed at which they were moving away from us, readable from the redshift of their light, he found that the relationship was linear. More distant galaxies moved away faster. The universe was expanding. Einstein, upon seeing the data, abandoned his cosmological constant and called its introduction his greatest blunder. The universe, it turned out, had no interest in remaining static. Hubble's original estimate for the expansion rate was approximately 500 kilometers per second per megaparsec. This was, as we would later discover, catastrophically wrong, but wrong in an instructive way. A Hubble constant of 500 would imply that the universe was only around 2 billion years old, which was already known at the time to be impossible, because geologists had determined that the Earth itself was older than that. The early measurement was wrong because Hubble's distance measurements were miscalibrated. But the underlying relationship, that recession velocity scales linearly with distance, was real and correct, and it launched the field of observational cosmology. Over the following decades, the Hubble constant was progressively revised downward. By the 1990s, two competing camps of astronomers had settled into an uneasy standoff. One group, led by Alan Sandage, Hubble's former assistant, measured H0 to be around 50 km per megaparsec. A second group, led by Gérard de Vaucouleurs, measured it to be around 100. The disparity was total. They were using the same universe and getting numbers that differed by a factor of 2. The Hubble constant was, to put it charitably, embarrassingly poorly known. A primary goal of the Hubble Space Telescope, named, with some irony, after the man whose original measurement was so far off, was to settle the question. And settle it to a first approximation it did. In 2001, the Hubble Key project delivered a value of 72 km per second per megaparsec, with an uncertainty of around 8%. The era of factor of 2 disagreements appeared to be over. It was not. The Hubble constant was about to become a battleground, not between two competing measurement teams, but between two fundamentally different ways of reading the universe. A conflict that would expose, for the first time, the possibility that the standard model of cosmology was not merely incomplete, but structurally wrong. Here is the shape of the problem. There are two ways to measure how fast the universe is expanding. One way is to look out into the nearby universe, within a few billion light years, and directly measure the recession velocities and distances of galaxies. This is called the local measurement. The other way is to look at the early universe, at light that left the cosmos when it was only 380,000 years old, and use our mathematical model of cosmic evolution to compute what the expansion rate must be today. This is called the early universe measurement. Both methods are rigorous. Both have been checked by multiple independent teams using different instruments and different mathematical approaches, and they disagree. The local measurement, championed most prominently by the team known as H0ES, the supernova H0 for the equation of state program, led by Adam Rias at Johns Hopkins University, places the Hubble constant at 73.04 ±1, or 4 kilometers per second per megaparsec. The early universe measurement derived primarily from data collected by the European Space Agency's Planck satellite, which mapped the cosmic microwave background with extraordinary precision between 2009 and 2013, places the Hubble constant at 67.4 ± 0.5 kilometers per second per megaparsec. Those two numbers look close. They are not. In the language of statistics, the discrepancy between them is measured in units of sigma, standard deviations, which describe how many times larger the gap is than the combined measurement uncertainties of both results. In 2011, the discrepancy was at roughly 3 sigma, meaning that the probability of both measurements being correct and the gap being a statistical accident was about 0.3%. By 2022, when the SH0ES team published what is now considered the definitive local measurement, the discrepancy had grown to more than 5 sigma. At 5 sigma, the probability of the disagreement arising by chance is below 1 in 3 million. In particle physics, a 5 sigma result is the standard threshold for declaring a discovery. In cosmology, it is the threshold for declaring a crisis. To feel the texture of this disagreement, consider what the two numbers actually imply. A universe expanding at 73 kilometers per second per megaparsec is around 5 billion years old. A universe expanding at 67.4 kilometers per second per megaparsec is around 13.8 billion years old. These are different universes in a meaningful sense. They have different amounts of time behind them. They have different histories. The same stars, the same galaxies, the same physics, but a different cosmic clock, and only one of those clocks can be right. This is, in my view, one of the most unsettling facts in all of modern science. Not because the numbers are exotic or the physics is violent, but because the two measurements are so careful, so thoroughly checked, so deeply grounded in independent physical principles that neither can be easily dismissed. What the Hubble tension is telling us, if we have the courage to listen, is that something is wrong, not with a calculation, not with an instrument, but with our model of the universe itself. To understand why the two methods give different answers, we need to walk through each one in some detail. The local measurement, the one that gives 73, works by building what cosmologists call the cosmic distance ladder. The term captures something true and something slightly terrifying about the technique. It is a structure of nested dependencies, each rung of the ladder calibrated against the one below it. If the lowest rung is wrong, every rung above it inherits that error, compounded. The distance ladder begins with parallax, the oldest and most fundamental technique in positional astronomy. Hold your finger up in front of your face and close one eye, then the other. Your finger appears to jump against the background. This is parallax, the apparent shift in the position of a nearby object relative to distant objects, as seen from two different vantage points. For nearby stars, we can measure their parallax by observing them from 2 points on Earth's orbit around the Sun, 6 months apart, 2 vantage points separated by approximately 299.2 million kilometers. The European Space Agency's Gaia satellite has measured the parallax of over 1 billion stars this way, with precisions in some cases approaching 10 microarcseconds. This is the bedrock. From parallax, we calibrate Cepheid variable stars, those breathing beacons first mapped by Henrietta Leavitt. We measure the parallax of nearby Cepheids in the Milky Way to establish their true brightness. Then we use those calibrated Cepheids to measure distances to other galaxies, where the Cepheids are too far for parallax to work, but close enough for us to resolve individual stars. And from those intermediate distance galaxies, we calibrate Type Ia supernovae, stellar explosions so bright they can be seen across billions of light years. Type Ia supernovae are not perfectly standardized candles, but they are standardizable. Their peak brightness can be inferred from the shape of their light curve, with enough precision to make them the most powerful distance indicators we possess for the deep universe. And it is from Type Ia supernovae, hundreds of them, scattered across billions of light years of cosmic volume, that the local measurement of H0 is ultimately derived. Every rung on this ladder has been checked. The S80ES team used the Hubble Space Telescope and, more recently, the James Webb Space Telescope to re-observe Cepheids in the galaxies they use to calibrate their supernovae. JWST's 4 times better spatial resolution than Hubble allowed the team to confirm that the Cepheids were being correctly identified and not confused with other stars at a confidence level of 8 sigma. The source of the high local value is not a simple measurement error. The SH0ES team has been extraordinarily careful. That is precisely what makes the tension so alarming. Now consider the early universe measurement, the one that gives 67.4. This method does not use stars at all, it uses sound. In the first 380,000 years after the Big Bang, the universe was a hot, dense plasma, a seething soup of protons, electrons and photons, so energetically entangled that light could not travel freely. Radiation pressure from the photons pushed outward against gravity, and this pressure-gravity competition drove sound waves, actual acoustic oscillations, through the plasma. These waves travelled outward from density fluctuations at a speed determined by the temperature and composition of the plasma. When the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, at a moment cosmologists call recombination, the sound waves froze, they stopped propagating, and the distance they had travelled in those 380 zeros and years, what cosmologists call the sound horizon, was imprinted into the universe as a preferred separation distance between clumps of matter. Today, nearly 13.8 billion years later, that frozen sound wave pattern is still visible. It appears as slight statistical enhancements in the large-scale clustering of galaxies. Galaxies are marginally more likely to be found at separations of approximately 500 million light-years, the stretched-out remnant of that original sound horizon. These acoustic ripples are called baryon acoustic oscillations. They are, in the most literal sense, the fossilized sound of the Big Bang, and they function as a standard ruler, a known physical length against which we can measure the expansion history of the universe. By comparing the apparent size of these ripples at different cosmic epochs, we can trace how space has expanded over time and extrapolate a value for H0 today. The Planck satellite measured the early universe version of these oscillations with extraordinary precision. The temperature variations in the cosmic microwave background form patterns whose angular scale depends directly on the sound horizon. Planck's value of H0 67.4 has been cross-checked by ground-based observatories, by the WMAP satellite before it, and by galaxy surveys that detect the baryon acoustic oscillation signal directly in the distribution of galaxies. DESI, the Dark Energy Spectroscopic Instrument, a telescope in Arizona equipped with 5 Zerosan swiveling robotic fiber optic eyes, measured 6 million galaxies in its first year alone and derived an independent H0 of 68.53 plus 0.8 erokilometers per second per megaparsec, entirely free of Planck data. This sits in 4 sigma tension with the SH0ES value. The two measurements are not just different numbers from different telescopes. They are different readings of different eras of cosmic history using fundamentally different physical phenomena, generating the same disagreement with extraordinary reproducibility. And that reproducibility is what separates the Hubble tension from an ordinary measurement problem and places it in the category of a genuine scientific crisis. 3 questions now hang open simultaneously. First, is the local measurement wrong? Is there some systematic error in the distance ladder that has not yet been found? Second, is the early universe measurement wrong? Is there some physics in the early universe that we have not accounted for, which has shifted the value of the sound horizon? Third is the standard model of cosmology itself, the lambda CDM model that has guided our understanding of the universe for 40 years, fundamentally incomplete. These questions will not all be answered tonight, but they are all open, and the implications of each answer are very different and very consequential. In most disagreements in science, one side is wrong and one side is right, and the resolution comes when we find the mistake. The Hubble tension is unusual because the most thorough analysis of both measurements, by both the groups who favour the higher value and the groups who favour the lower, has failed to find a compelling error on either side. This has moved cosmologists from the comfortable zone of someone made a mistake into the far more dangerous zone of both measurements are correct and the standard model is broken. Let's stress test the local measurement first, because it has the most rungs on its ladder and therefore the most opportunities for error to accumulate. The cosmic distance ladder used by the SH0ES team rests on 4 geometric anchors, 4 points in the universe whose distances are known not from any other astronomical object, but from pure geometry, from the basic physics of orbital mechanics and wave propagation. The first anchor is parallax measurements from Gaia of Cepheid variable stars within the Milky Way. The second is a group of detached eclipsing binary stars in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, about 163,000 light-years away. These binary star systems are essentially orbital clocks. We can measure the orbital parameters of the 2 stars from spectroscopy, compute their physical sizes from the dynamics, measure their angular sizes from photometry, and derive the distance to the system directly and geometrically. No assumptions about stellar physics are required. The distance to the Large Magellanic Cloud derived from these eclipsing binaries is 49, 590 plus 540 light-years, precise to 1.1%. The third anchor is a similar group of eclipsing binaries in the Small Magellanic Cloud. The fourth is the Megamesa galaxy NGC 4258, a galaxy 23.5 million light-years away, in whose centre a supermassive black hole is surrounded by a warped disk of gas that emits microwave radiation at 22.235 GHz, the frequency associated with water molecules undergoing stimulated emission. These water masers orbit the black hole, and their orbital dynamics can be measured with extraordinary precision using very long baseline radio interferometry. From the period and velocity of the maser orbits, and from the measured angular size of the disk, the distance to NGC 4258 follows from pure orbital mechanics, independent of any stellar physics or distance ladder. The distance is 23.5 megaparsecs, and when the SH0S team uses that geometric distance to calibrate their Cepheid measurements in that same galaxy, they get Cepheid luminosities consistent with those derived from the Gaia parallaxes and the Magellanic Cloud eclipsing binaries, to within fractions of a percent. The next rung up the ladder involves 37 host galaxies that contain both observable Cepheid variable stars and at least one Type Ia supernova that has been recorded in the historical photometric record. These are the calibration galaxies. In each of them, the SH0S team uses Cepheids to measure the distance, then uses that distance to determine the absolute peak luminosity of the Type Ia supernova that occurred in that galaxy. 42 supernovae in 37 host galaxies give 42 calibrated absolute magnitudes. These are then compared to hundreds of Type Ia supernovae in the distant Hubble flow, galaxies so far away that their recession velocity is overwhelmingly dominated by cosmic expansion and not by any local gravitational perturbation. From the ratio of apparent brightness to the expected absolute brightness, derived from the calibration sample, the Hubble constant follows directly. Every step of this process has been scrutinized. The possibility that Cepheids observed in distant galaxies are being confused with other stars, blended with background or companion stars in the crowded stellar fields of other galaxies, was the single most popular proposed systematic error. It was ruled out at 8 sigma by JWST observations that resolved individual Cepheids at a resolution impossible for Hubble. The possibility of metallicity effects, that Cepheids in galaxies with different chemical compositions might have different luminosities than the Milky Way Cepheids used as the calibration base has been studied extensively. It shifts the result by fractions of a percent, not by several kilometers per second per megaparsec. The possibility that the geometric anchors themselves are miscalibrated has been tested by using different subsets of them in isolation. The answer doesn't change, and yet the answer keeps coming out high every time the SH0S team has added more data, more geometric anchors, more calibration galaxies, more supernova host galaxies. The Hubble constant has stubbornly near 73. The uncertainty has shrunk. The central value has not moved. Now stress test the early universe measurement. The Planck satellite's measurement of H0 is not a direct measurement at all. It is an inference, a value derived by feeding the cosmic microwave background data into a specific mathematical model, the lambda CDM model, and asking what value of H0 best fits the data within that model. The CMB itself does not directly tell us H0. It tells us a combination of parameters, and H0 is extracted from those combinations via the model. If the model is wrong, if, for example, some physical ingredient is missing from the description of the early universe, then the CMB can give us a precisely wrong answer rather than an imprecise right one. This is not a trivial concern. The lambda CDM model has 6 free parameters. It describes the universe in terms of the density of ordinary matter, the density of dark matter, the density of dark energy, the curvature of space, the amplitude of the initial density fluctuations, and the spectral tilt of those fluctuations. The model was constructed from first principles to be the simplest possible description consistent with the observations available in the early 2000s. It is not a law of nature. It is a model, a deliberately simplified representation of a far more complex reality. Here is the specific vulnerability, the sound horizon, the physical ruler that underlies all early universe measurements of H0 depends on conditions in the universe before recombination. Specifically, it depends on the density of photons, baryons, and dark matter in those first 380,000 years. If there was any additional source of energy density in the early universe, some new particle, some new field, some new physical process, it would have altered the rate of expansion in that era, which would have changed the sound horizon, which would have changed the value of H0 that Planck extrapolates to today. This is the opening for new physics on the early universe side, and several candidates have been proposed. The most widely discussed is called early dark energy, a hypothetical component that would have contributed a burst of dark energy-like expansion in the period immediately before recombination, boosting the expansion rate just enough to shrink the sound horizon by the right amount, raising the Planck-inferred H0 closer to the SH0ES value. Early dark energy models can in principle resolve the Hubble tension. The problem is that they create new tensions. Adding early dark energy to the lambda CDM model improves the H0 agreement, but worsens the fit to other cosmological observables, specifically to the amplitude of large-scale structure in the universe, a quantity measured by a separate parameter called S-stray. Fixing one crack opens another. The standard model is beginning to resemble a container that leaks no matter where you seal it. There is a second class of proposed solutions that lives on the late universe side. If dark energy, the mysterious energy responsible for the accelerating expansion of the universe, is not constant as the lambda CDM model assumes, but instead changes over time, then the relationship between the observed baryon acoustic oscillation signal in galaxy surveys and the computed value of H0 could shift. Some variants of evolving dark energy could in principle bring the two measurements into agreement. But as we will see, the evidence for evolving dark energy has now taken on a life of its own that is, in some ways, even more alarming than the Hubble tension. What is beginning to feel unavoidable to any cosmologist working in this field is the conclusion that the lambda CDM model, the 6-parameter framework that has guided our understanding of the universe since the turn of the millennium, is not complete. Something is missing, something significant, and that missing something has to live in the equations in a way that simultaneously explains the Hubble tension, preserves the other successes of lambda CDM and does not create new predictions that contradict observations we haven't yet made. That is an extraordinarily narrow needle to thread. No proposed model has done it yet, and while the theorists search for that needle, the observers are accumulating a second, separate anomaly, one that has emerged from the deepest galaxy surveys ever attempted, using an instrument that is rewriting our picture of the early universe. Before we can appreciate what the dark energy spectroscopic instrument has found, we need to understand what dark energy is, or rather, what it was supposed to be, because the story of dark energy begins with one of the most spectacular and counterintuitive discoveries in the history of astronomy, made in 1998 by two competing teams of physicists who were, at the time, expecting to find the exact opposite of what they found. In the mid-1990s, the dominant question in cosmology was this: how fast is the universe decelerating? Everyone assumed the expansion was slowing down. The Big Bang had given the universe its initial velocity, and gravity, the mutual attraction of all matter for all other matter, was acting as a brake. The only question was whether gravity was strong enough to eventually reverse the expansion and cause the universe to collapse in a big crunch, or whether it would slow the expansion gradually and asymptotically, leaving the universe expanding forever at an ever-diminishing rate. No one seriously entertained the possibility that the universe might be accelerating. Two independent research teams set out to measure the deceleration rate by observing Type Ia supernovae at extreme distances, looking back in time so far that they could trace the expansion history of the universe across billions of years. One team was led by Saul Perlmutter at Lawrence Berkeley National Laboratory. The other was led by Brian Schmidt at the Australian National University, with a key theoretical contribution from Adam Rias, then a doctoral student at Harvard. The two teams were fierce rivals, motivated partly by competition and partly by the awareness that what they were attempting, measuring the geometry of the universe using exploding stars at the edge of the observable cosmos, had never been done before. What Perlmutter's team expected to find when they looked at supernovae at redshifts above 0.5, meaning that the universe had expanded by more than 50% since the light from those supernovae was emitted, was that the supernovae were slightly brighter than a coasting universe would predict. Brighter because, if the universe was decelerating, it had been expanding faster in the past than it is now, meaning the supernova had not travelled quite as far as a coasting universe calculation would suggest. Brighter means closer. Closer means deceleration. Instead, both teams found the supernovae to be dimmer than expected. Dimmer means more distant than expected. More distant means the universe had been expanding more slowly in the past than it is now. The expansion was accelerating. This result was so far outside the bounds of what anyone had anticipated that both teams initially suspected instrumental error or some poorly understood property of Type Ia supernovae themselves. Rias, going through the Schmidt team's data, found the same result independently. When both teams published in 1998 and 1999, Rias's paper on February 22, 1998, in the Astronomical Journal, Perlmutter's companion paper the following year, the scientific community was, to put it charitably, sceptical. The result earned Perlmutter, Schmidt and Rias the Nobel Prize in Physics in 2011. By that point, the accelerating expansion had been confirmed by a dozen independent lines of evidence, and the skepticism had given way to a bewilderment that has never really resolved. What is pushing the universe apart? The name we gave it, dark energy, is less a description than an admission of ignorance. It is dark in the sense of being unknown, not in the sense of being dark-coloured. It carries negative pressure, a property that, in the context of general relativity, causes it to drive expansion rather than oppose it. Its energy density, insofar as we can measure it, appears to make up approximately 68% of the total energy content of the universe. The remaining 27% is dark matter, also unknown, and a mere 5% is the ordinary matter of which stars, planets and people are made. We are, in the most literal accounting, a marginal component of our own universe. The simplest and most elegant explanation for dark energy is that it is the energy of the vacuum, the irreducible minimum energy that quantum field theory demands must be present even in apparently empty space. This is Einstein's cosmological constant, Lie resurrected from its grave of greatest blunders and given a new identity. In the lambda CDM model, Lie is a fixed constant. Its value does not change, it does not evolve. It has been the same since the earliest moment of cosmic history, and will remain the same until the universe's last exhale billions upon billions of years from now. The energy of the vacuum is simply a property of space itself, unchanging and uniform. The problem is that quantum field theory predicts a value for the vacuum energy density that is approximately 10 squared the far times larger than the value we observe. This is not a rounding error. It is the largest discrepancy between a theoretical prediction and an experimental measurement in the entire history of science, by orders of magnitude too large to contemplate without a certain existential vertigo. The cosmological constant problem, the question of why the vacuum energy is so small, is widely considered the deepest unsolved problem in theoretical physics. We do not know why Lie has the value it has. We cannot derive it. We simply measure it and insert it into our equations, and the equations work. For now. But what if Lau is not constant? What if dark energy is not the static energy of the vacuum, but something more dynamic? A field that evolves over time, thickening and thinning as the universe ages, perhaps even responding to the expansion of the cosmos in ways we have not yet modelled. This possibility has a name, quintessence, and it has a problem. We have had no clear observational evidence for the past 2 decades that dark energy has changed at all. Until now, in April 2024, the DESI collaboration released the results of their first year of observing. DESI sits atop Kitt Peak in the Sonoran Desert of Arizona, at an elevation of 2,096 meters. Its focal plane contains 5 zero-zo independently controllable robotic positioners, each one carrying a fiber optic cable. In a single night, these 5,000 robots swivel to point their fibers at 5,000 different galaxies simultaneously, collecting spectra that reveal each galaxy's redshift, its recession velocity, to extraordinary precision. In its first year, DESI observed 6 million galaxies and quasars spanning the last 11 billion years of cosmic history. From this galaxy map, the DESI team extracted the baryon acoustic oscillation signal, those fossilized sound waves, at multiple different cosmic epochs, essentially taking snapshots of the universe's expansion history at different moments in time. And when they compared the expansion history across those snapshots to what the lambda CDM model predicted, they found a discrepancy. The discrepancy was not enormous. It was at the level of 3.4 sigma, which is suggestive but not definitive. But it pointed in a specific direction. Dark energy appeared to have been somewhat stronger in the past and slightly weaker in the recent past. Not a cosmological constant, something that evolves. This sent a tremor through the cosmological community, but the cautious among them noted that 3.4 sigma anomalies have a way of disappearing when more data arrives. The DESI team itself was studiously measured in its language. They spoke of ints and indications, not discoveries. The community waited. In March 2025, DESI released the results of 3 full years of observing, a dataset spanning 14.9 million galaxies and quasars, more than double the previous sample. The team had spent months testing their analysis pipeline on scrambled versions of the data, looking for bugs, testing for bias. On December 10, 2024, representatives of the collaboration gathered in Cancun, Mexico, spent 3 hours in deliberation, and then retired to their hotel rooms to unscramble the data. Seshadri Nadatha, a cosmologist at the University of Portsmouth, who was among those who saw the result first, later described it as the best experience of my professional career. The signal was still there, stronger. The tension with lambda CDM, with the assumption of a cosmological constant, had grown to 2 sigma when DESI's galaxy data was combined with existing supernova catalogues and cosmic microwave background observations. At 4.2 sigma, The probability of this result arising by chance under a constant dark energy universe is approximately 1 in 30,000. These are odds comparable to flipping a fair coin 15 times in a row and getting 15 heads. The Dark Energy Survey, a separate collaboration using a telescope in the Chilean Andes, simultaneously published results from 5 years of observations, including the most extensive catalogue of supernovae ever compiled. Their independent analysis found a tension with lambda CDM of 3.2 sigma that effectively disappeared when dark energy was allowed to evolve. "This paints a nice consistent picture," said Michael Troxell of Duke University, a member of the DS team. 2 independent experiments, 2 independent datasets, 2 independent methods. The same conclusion. What makes this result specifically alarming rather than merely exciting is the direction of the evolution. The DESI data suggests that dark energy was stronger several billion years ago and has been weakening since, in the parametric language cosmologists use to describe this, in the so-called W0WA parameter space, where W is the equation of state parameter of dark energy. The data sits in a region that requires dark energy to have crossed a boundary called the phantom divide. At one point in cosmic history, the data suggests dark energy was behaving like what theorists call phantom dark energy, energy with an equation of state parameter below 1, which is physically very difficult to achieve with any conventional field theory and which, if it persisted, would ultimately lead to what cosmologists have named the Big Rip, a scenario in which the accelerating expansion tears apart first galaxy clusters, then individual galaxies, then star systems, then planets, then atoms, until the universe is reduced to a soup of disconnected particles, each one isolated in its own expanding bubble of space. The Big Rip is not a prediction of the current data. The DESI signal is not strong enough to point conclusively to any specific fate. But what the data is saying, with increasing confidence, is that the simplest possible description of dark energy, a constant, a number, a fixed property of the vacuum, may not be correct. And if that simplest description is wrong, then lambda CDM, the framework within which every cosmological observation of the past 20 years has been interpreted, is wrong, not wrong in the trivial sense of being an approximation that can be refined. Wrong in the sense of missing something fundamental, some ingredient, some process, some force that has been shaping the fate of the universe all along. This is where 2 crises in cosmology meet: the Hubble tension, the discrepancy in the expansion rate, and the dark energy anomaly, the evidence for evolution in the universe's dominant energy component, are not obviously the same problem, but they are both pointing in the same direction. They are both signs that the lambda CDM model, for all its extraordinary successes, is cracking under the weight of precision measurements. The next question, the one that keeps cosmologists awake, is whether those cracks can be repaired, or whether they are the first visible fractures in a structure that needs to be rebuilt from the ground up. This is, to my mind, one of the most consequential junctures in the history of science. We are not refining the details of a complete theory. We are confronting the possibility that the complete theory does not yet exist. In 2019, a paper appeared in the Astrophysical Journal that did something almost no paper in modern cosmology manages to do. It complicated the Hubble tension rather than clarifying it. Not because it was wrong, but because it was right in a way that made everything more difficult. The paper was authored by Wendy Friedman of the University of Chicago, Barry Madore, and the team of the Carnegie Chicago Hubble program, and the number they reported for the Hubble constant, 69.8 +0.8 kilometers per second per megaparsec, sat directly between the 2 warring camps, agreeing with neither and comforting no one. Wendy Friedman is not a person who seeks drama. She has spent more than 4 decades in the measured, painstaking world of extragalactic distance measurement, and she has earned a reputation for exceptional care. She was a co-leader of the Hubble Key project, the multi-year international collaboration that used the newly launched Hubble Space Telescope to measure the Hubble constant to an accuracy of 10%, delivering the 72 kilometers per second per megaparsec value in 2001 that seemed at the time to be the end of the road. She has received the Gruber Prize in Cosmology, the Harvey Prize, and honorary degrees from universities on 3 continents. She is not easily dismissed. But Friedman is also something rarer in the culture of precision science. She is constitutionally unwilling to let an anomaly slide, where other scientists see a discrepancy and reach first for the explanation that makes it go away. Friedman reaches for a different calibration, a different standard candle, a different physical anchor, not because she distrusts her colleagues, but because she distrusts the seductiveness of a clean answer. Science, she has said in public lectures, is not about finding the answer you expected. It is about finding the answer. Her work in the late 2010s was motivated by a specific concern about the SH0E's distance ladder, its reliance on Cepheid variable stars as the intermediate calibration step. Cephids are extraordinary standard candles, but they are not simple ones. Their luminosity period relation, the foundational formula that makes them useful for measuring distances, varies with the chemical composition of the star. Cephids in metal-rich environments pulse differently than Cephids in metal-poor ones. Correcting for this metallicity dependence requires models, and models introduce assumptions, and assumptions, however well-grounded, propagate uncertainties in ways that are difficult to fully quantify. Friedman was not suggesting that the SH0ES team had done anything wrong. She was suggesting that an entirely different type of standard candle, calibrated independently of Cephids, might tell us something different. The alternative she chose was the tip of the red giant branch, the TRGB. When a low-mass star has exhausted the hydrogen in its core, it swells into a red giant, growing steadily brighter over millions of years as its helium core contracts under gravity and the temperature rises. At the moment the core temperature reaches approximately 100 million Kelvin, helium fusion ignites in a sudden violent thermal runaway known as the helium flash. Before this moment the star brightens. At this moment its luminosity peaks at a precise and nearly universal value, approximately 270 million times the luminosity of the Sun, across a remarkably narrow range, and then it rapidly fades as the helium fusion stabilizes. The peak brightness at the tip of the red giant branch is therefore a standard candle, one that depends on the nuclear physics of helium ignition rather than on any stellar pulsation model. Friedman's team measured the TRGB in a set of galaxies carefully chosen to overlap with the SH0ES supernova sample, allowing a direct comparison. When their analysis was complete, they found H0 69.8. This number was significantly lower than the SH0ES value of 73, but significantly higher than the Planck value of 67.4. It suggested, provocatively, that either the Cepheid calibration or the TRGB calibration, or possibly both, carried systematic errors that had not been identified. The reaction from the SH0's team was swift and pointed. Adam Rias and colleagues published a reanalysis of the TRGB data and concluded that the Carnegie-Chicago team had applied an incorrect geometric zero-point calibration, effectively misidentifying the precise luminosity of the TRGB in the reference galaxy NGC 4258. When the reanalysis used the same data but a corrected zero-point, the TRGB result shifted upward to approximately 71, 5 km per second per megaparsec, closer to the SH0E's value but still not matching it. Friedman's response was methodical. She did not simply defend her original analysis, she went further. In 2024, she published a new set of results using 3 independent calibrators simultaneously: Cephids, the TRGB, and a third entirely independent distance indicator called the J-band asymptotic giant branch, or JAGB. The JAGB method uses carbon-rich stars that occupy a particular position on the asymptotic giant branch of stellar evolution, a position associated with a nearly constant infrared luminosity that can serve as a standard candle independent of both stellar pulsation and nuclear phase transitions. 3 independent calibrators, 3 different physical processes, 3 different sets of systematic errors. All 3, Friedman's team reported, yielded a Hubble constant between 69 and 70 km per second per megaparsec, below 73. above 67.4, stubbornly, persistently sitting in the middle. What this means for the Hubble tension is uncomfortable and important. If the TRGB and JB results are correct, if there is a systematic error in the Cepheid-based SH0ES measurement that inflates it, then the true local Hubble constant might be closer to 70, and the tension with Planck would shrink from 5 sigma to something around 2 sigma, which is statistically manageable. The crisis would diminish. But the SH0ES team, using JWST data, has continued to find their Cepheid measurements reliable and consistent, ruling out blending and metallicity biases at high confidence. The two analyses are using the same universe and finding different answers, and at the heart of that discrepancy is a set of calibration choices about geometric anchors, about the 0 point of the TRGB luminosity, about the properties of carbon-rich stars that reflect genuine scientific uncertainty, not error on either side. I will admit, when I first went through the details of the Friedmann SH0ES dispute, I had to put my notes down for a while and sit with the implications. This is not a story of someone being right and someone being wrong. This is a story of two groups of extraordinarily capable scientists looking at the same night sky through different methodological lenses and finding that precision is not the same thing as accuracy. The numbers are precise, the uncertainties are real, the disagreement is genuine, and it points to something that no amount of additional observation can fully resolve without a conceptual breakthrough. We do not fully understand the systematic biases in our own measurement techniques at the level of precision the Hubble tension requires us to. The James Webb Space Telescope has now observed 20 of the 37 host galaxies used by the SH0's team for their Cepheid calibration. In every case, the Cepheid measurements have agreed with the previous Hubble observations to within the quoted uncertainties, with no evidence of the blending or contamination that had been the most popular proposed explanation for the high SH0ES value. But the JWST data has not yet been used to perform a full end-to-end remeasurement of the Hubble constant using the TRGB or JB methods at the precision the Hubble tension requires. That analysis is coming. When it arrives, it will either narrow the gap between the competing methods or deepen it. Either outcome will tell us something important. What Wendy Friedman's story illustrates, beyond the technical details, is something about the texture of science at its frontier. The resolution of the Hubble tension will not come from one heroic measurement. It will come from the slow accumulation of independent constraints, from different groups, using different methods arriving at answers that either converge or continue to diverge, and from the willingness of scientists to follow the numbers wherever they lead, even when those numbers are pointing at something the standard model doesn't have room for. Friedmann, for her part, has stated publicly that she believes the Hubble tension is real, that it is not a statistical artifact, and that it likely requires new physics. She does not know what that new physics is, neither does anyone else. But she is, in the very specific way that makes scientists indispensable, looking. 40 years ago, cosmology was a field that operated with what its practitioners sometimes called the factor of 2 problem, the acknowledgement that even the most fundamental quantities in the subject were known only to within a factor of 2 in either direction. Today, we know the age of the universe to a fraction of a percent. We know the composition of the universe to better than 1%. We know the geometry of space, whether the universe is flat, open, or closed, to a precision that would have seemed science fiction to the cosmologists of 1985. This transformation was made possible by one instrument above all others, the Planck satellite. Launched by the European Space Agency on May 14, 2009, Planck spent 4 years orbiting the second Lagrange point of the Earth-Sun system, a gravitationally stable location 5 million kilometers from Earth in the direction away from the Sun, where an object can maintain a constant position relative to both Earth and Sun with minimal fuel expenditure. From that position, shielded from the thermal contamination of the Sun and the Earth, Planck's detectors were cooled to 0.1 Kelvin, 1/10 of a degree above absolute zero, the lowest operational temperature of any object humans have ever placed in space, and pointed systematically across the entire sky for 9 scanning cycles. What Planck was measuring is the most ancient light in the universe, and the cosmos was 380,000 years old, a moment that feels impossibly recent against the backdrop of 13.8 billion years of subsequent history, but which was in fact an era that lasted longer than recorded human civilization. The universe cooled below the threshold at which protons and electrons could remain separate. They combined into neutral hydrogen atoms. The plasma became transparent. Photons that had previously been pinballing through the charged soup in a constant chain of Compton scattering were suddenly free to travel in straight lines. And they have been travelling in straight lines ever since. For 13.8 billion years, their wavelengths stretched by cosmic expansion from the short wavelengths of visible light into the microwave range, the range used by kitchen microwave ovens. Until today, they arrive at our detectors as a nearly uniform background of thermal radiation at a temperature of 2.72548 Kelvin, measured in every direction of the sky. The word nearly in that previous sentence is where all the physics lives. The cosmic microwave background is not perfectly uniform. It has tiny temperature fluctuations, variations of roughly 1 part in 100,000, that represent the quantum fluctuations of the earliest moments of the universe, stretched to cosmic size by the subsequent expansion. These fluctuations are the seeds from which all structure in the universe grew. The slight overdensities became galaxy clusters, the underdensities became voids, and superimposed on this statistical map of primordial structure are the acoustic oscillation patterns, the imprints of those pressure waves that propagated through the plasma before recombination. Planck measured these temperature variations across the entire sky, with unprecedented angular resolution and sensitivity. The resulting angular power spectrum, a graph of how much variation there is at each angular scale, is covered with peaks and troughs, each one a harmonic of the fundamental sound horizon, each one carrying information about the physical conditions of the early universe. By fitting the 6-parameter lambda CDM model to these peaks, the Planck team extracted values for every cosmological parameter with a precision that was, in 2013 when the first results were published, nothing short of revolutionary. The age of the universe, 13.813 plus minus 0.038 billion years. The density of ordinary matter, 4.93% of the total. The density of dark matter, 26.8%. The density of dark energy, 68.3%. The Hubble Constant, 67.4 plus minus 0.5 km per second per megaparsec. These numbers have held up every subsequent analysis of the Planck data, and there have been many by independent teams, has reproduced essentially the same values. The Atacama Cosmology Telescope, a ground-based instrument in the Chilean Andes that observed the CMB with different systematics and a different frequency coverage, independently measured H0 67.6 plus 1.1 in combination with WMAP data and 68.2 plus or minus 1 in combination with the South Pole Telescope. These are all consistent with each other and with Planck, and they are all inconsistent with the SH0's value of 73.04, the specific mathematical machinery by which the CMB constrains H0 runs through the sound horizon. The Planck data precisely measures the angular scale of the first acoustic peak, the scale at which temperature fluctuations are largest, corresponding to the sound horizon as seen from our present vantage point. This angular scale is the ratio of the sound horizon's physical size to the distance the CMB photons have travelled to reach us. To convert this angular measurement into a value for H0, we need to know the physical size of the sound horizon. And the physical size of the sound horizon depends on how fast the universe was expanding before recombination, which depends on the energy content of the universe at that time, which the Planck data itself measures from other features of the CMB power spectrum. The measurement is self-consistent within the lambda CDM framework. Here is the critical vulnerability, and I want to be precise about it, because it is the gateway to new physics. The sound horizon scales approximately as the inverse of the expansion rate in the pre-recombination era. If the universe was expanding faster before recombination than lambda CDM predicts, faster for example, because there was an additional source of energy density in that era that the model doesn't account for, then the sound waves had less time to travel before the plasma froze, and the sound horizon would be smaller. A smaller sound horizon, observed at the same angular scale, implies that the CMB photons have travelled a shorter distance to reach us. A shorter distance means a faster expansion rate. A faster expansion rate means a higher H0. This is the principle behind early dark energy models. Inject extra energy into the pre-recombination universe, shrink the sound horizon, and raise the CMB inferred H0 toward the SH0es value. The challenge for early dark energy is not conceptual but quantitative. The extra energy density needed to shift H0 from 67, 4 to 73 is substantial, roughly a few percent of the total energy density at the time of recombination. That extra energy density would have had physical effects beyond simply changing the sound horizon. It would have altered the height ratios of the acoustic peaks. It would have changed the amplitude of small-scale CMB fluctuations. It would have modified the subsequent growth of cosmic structure in the late universe, and it would therefore have left fingerprints in observables that are now measured with high precision. When theorists build early dark energy models and confront them with all available data, not just the CMB, not just the galaxy surveys, but all of it simultaneously, they find that the models can be tuned to fit the Hubble tension, but at the cost of worsening the fit to some other observable, most notably Astray, the parameter that describes the amplitude of matter fluctuations on scales of 8 megaparsecs. The Astray tension, a separate discrepancy in which the observed clustering of matter in the late universe is somewhat lower than lambda CDM predicts, has an opposite sensitivity to early dark energy. The extra energy density that helps with H0 tends to make the Astray problem worse. The standard model is under siege on two fronts simultaneously, and the proposed resolutions on one front tend to open a new breach on the other. There is a second class of new physics proposals that focuses not on the pre-recombination era but on the post-recombination era, specifically on the possibility that the gravitational constant itself is not constant, or that dark energy interacts with dark matter in some way that modifies the late universe expansion history. These proposals generally do worse than the early dark energy models at fitting the full data combination because the baryon acoustic oscillation measurements from galaxy surveys like DESI constrain the late universe expansion history so tightly that any substantial modification to it shows up immediately. The most striking theoretical development of recent years is the suggestion, articulated most forcefully by string theorists including Kamran Vafa at Harvard, that a stable vacuum with a positive cosmological constant might not be achievable in the quantum gravity framework of string theory at all. Vafa's swampland conjectures, a set of proposed constraints on which physical theories are consistent with quantum gravity, suggest that any de Sitter space, any universe with a positive and constant cosmological constant, is inherently unstable. Universes of this type eventually decay into other states. This would mean that the cosmological constant is not truly constant. It must evolve, eventually declining towards zero or becoming negative. And if that is correct, the DESI's observation of weakening dark energy is not an anomaly. It is an observation of the universe doing exactly what string theory demands it must eventually do. This is where the picture becomes simultaneously thrilling and vertiginous. Two anomalies in cosmological data, the Hubble tension and the dark energy evolution, are individually alarming. Together, they paint a portrait of a standard model under pressure from multiple directions. The pressure has not yet cracked the dam, but the water is rising, and the next few years, with results from DESI's complete 5-year survey, from the Euclid Space Telescope that launched in 2023, and from the Rubin Observatory's legacy survey of space and time beginning its full operations, will bring either a resolution or a deepening of a crisis that is already the most profound in cosmology, in a generation. What is the highest possible stake in all of this? It is nothing less than the fate of the universe. If dark energy is evolving and weakening, then the accelerating expansion that has been pushing galaxies apart may not be permanent. The future is open in a way it wasn't before. The universe might decelerate again. Gravity might reassert itself on cosmic scales. The Big Rip recedes, other endings, stranger, more exotic, less explored, take its place. We are not merely measuring a constant, we are reading the future. The Lambda CDM model has earned its status as the standard model of cosmology through a century of increasingly precise agreement with observation. It describes, with 6 numbers, how a universe born in a hot, dense state 13, 8 billion years ago evolved into the structure we observe today, a web of galaxy filaments and voids spanning hundreds of millions of light years, punctuated by galaxy clusters containing trillions of stars each cluster embedded in a halo of invisible dark matter that provides the gravitational scaffolding for everything visible. Lambda CDM predicted the acoustic peaks in the CMB before they were measured. It predicted the baryon acoustic oscillation signal in galaxy surveys before it was detected. It predicted the abundance of light elements forged in the first 3 minutes: hydrogen, helium, and lithium, with extraordinary precision. It is not a framework that should be discarded lightly. But the Hubble tension, the dark energy evolution, and a growing catalogue of smaller anomalies are now forcing the community to examine it with a rigour that was previously unnecessary. The proposed solutions to the Hubble tension fall into 3 broad categories. The first is mundane, a systematic error. The second is exotic, new physics in the early universe. The third is radical, new physics that modifies general relativity itself. Let us go through each. The mundane explanation, systematic error, remains on the table, though it has been dramatically narrowed. The most credible version of the systematic error hypothesis focuses on the Cepheid calibration step in the SH0E's distance ladder. Cepheid variable stars are measured in the crowded stellar environments of other galaxies, where individual stars at distances of tens of millions of light years are separated by fractions of an arcsecond on the sky. At Hubble Space Telescope resolution, there is a real possibility that some of the light attributed to a target Cepheid is actually coming from unresolved companion stars in the background or foreground, a phenomenon called crowding or blending. If this effect is systematic, if it consistently makes Cepheids appear brighter than they truly are, then the distances derived from those Cepheids would be underestimated, and the derived Hubble constant would be overestimated. This hypothesis was the dominant proposed explanation for the Hubble tension for most of the 2010s. It was plausible, it was specific, and it was testable. The James Webb Space Telescope, with its dramatically superior angular resolution in the near-infrared, where Cepheids are brightest and dust absorption is minimized, was designed in part to test it, and test it did. WST observations of Cepheids in 20 of the 37 SH0ES host galaxies confirmed the Hubble measurements with a residual scatter reduced by a factor of 2.5. The blending hypothesis was ruled out as an explanation for the Hubble tension at 8 sigma. This does not mean there is no systematic error anywhere in the SH0S analysis, but it does mean that the most appealing, most specific, most physics-motivated version of the systematic error hypothesis has been falsified. The alternative systematic error proposals are less focused and harder to test. One suggestion is that type Ia supernovae in the local calibration sample behave subtly differently from type Ia supernovae in the distant Hubble flow sample, that there is some evolution in the properties of the supernova progenitor systems, with redshift that has not been fully characterized. This is not implausible. The environments in which stars form and evolve change systematically with cosmic time. High redshift galaxies tend to be younger, more metal-poor, and more actively star-forming than local galaxies. If the properties of the white dwarf progenitors of type Ia supernovae, their mass, their companion star type, their metallicity, depend on these environmental factors, then the average luminosity of a Type Ia supernova at 0.5 might be marginally different from one at 0.1. Studies of supernovae in host galaxies of different masses, star formation rate, and metallicities have found evidence of such host galaxy corrections, and different teams apply these corrections differently. But the magnitude of the effect is insufficiently large to close the 5 sigma gap between the SH0s value and Planck. Another systematic error proposal targets the TRGB calibration. As described in the previous chapter, the Friedman team's TRGB results and the SH0s team's reanalysis disagree on the absolute calibration of the TRGB luminosity in the reference galaxy NGC 4258. The physical source of this disagreement, whether it is caused by an asymmetry in the luminosity function of red giant branch stars near the tip, by population dependencies in the TRGB luminosity itself, or by measurement noise, remains contested. JWST observations of a larger sample of TRGB calibrators should eventually resolve this, but the dataset is not yet complete. Until it is, the TRGB versus Cepheid debate will remain open. Perhaps the most underappreciated systematic error hypothesis involves the local universe itself. The possibility that the Milky Way and its immediate cosmic neighbourhood occupy a region of the universe that is, for reasons of large-scale structure, expanding slightly faster than the cosmic average. This is called the local void hypothesis. Our galaxy sits near the edge of a large underdense region, a cosmic void, that spans approximately 200 to 300 megaparsecs. Voids expand faster than the cosmic average because the deficit of mass within them means they are less gravitationally retarded. If the distance ladder measurements are conducted primarily within this void, which they largely are, since the Cepheid observable galaxies and the supernova calibration galaxies are all relatively nearby, then the measured expansion rate might be biased high relative to the true cosmic average. The void hypothesis predicts a correction to the Hubble constant on the order of a few percent in the direction of lowering the local value, which is qualitatively the right direction. Quantitative modelling of the local voids effect on H0 has not yet produced a number large enough or precise enough to close the tension on its own. Moving now to the second category, new physics in the early universe. The early dark energy scenario has already been introduced, but it deserves a more complete treatment of its theoretical landscape. Early dark energy is not a single model, it is a family of models, united by the mechanism of injecting an additional energy density into the universe at or before recombination. The simplest versions invoke a scalar field, a hypothetical field that permeates all of space and carries potential energy, that is initially trapped near a maximum of its potential energy function by the high energy conditions of the early universe, then rolls down its potential as the universe expands and cools, releasing its energy density in a burst near the time of recombination, and then diluting away as the universe continues to expand. The scalar field is engineered so that its energy density peaks near the right epoch and decays rapidly enough to avoid leaving observable traces in the post-recombination universe. The challenge is threading this needle while simultaneously matching all the other data. The acoustic peak heights and their ratios in the CMB are extremely sensitive to the matter-radiation ratio at recombination, something that early dark energy modifications at the percent level would change. Ground-based CMB experiments like the Atacama Cosmology telescope have measured the small-scale CMB power spectrum, the part of the spectrum that is most sensitive to these changes, with sufficient precision to constrain many early dark energy models. The constraints are tight but not yet fatal. Some models survive. The question is whether the surviving models are well motivated from a particle physics perspective, or are engineered solely to fit the data, a distinction that bears on how seriously the theoretical community treats them. A more exotic early universe solution involves an additional relativistic component, effectively an extra neutrino-like species that contributes to the energy density of the universe in the pre-recombination era. This is parameterized in cosmological models as a change in the effective number of relativistic species, denoted NEF. The standard model of particle physics predicts NeF 3.044 corresponding to the 3 known neutrino flavors with corrections for quantum effects at neutrino decoupling. If NeF were somewhat higher, if there were, for example, a sterile neutrino or a new type of dark radiation, the expansion rate before recombination would be higher, the sound horizon would be smaller, and the CMB inferred H0 would shift upward. However, Big Bang nucleosynthesis, the process by which hydrogen, helium and lithium were forged in the first 3 minutes, is also sensitive to NeF, because the neutron-to-proton ratio at nucleosynthesis depends on the expansion rate at that epoch. The precisely measured abundance of helium-4 in primordial environments constrains NeF to be close to 3.044. An extra-sterile neutrino that could solve the Hubble tension would produce more helium than is observed. The door is not closed, the constraint allows some room, but it is significantly narrower than the Hubble tension alone would require. The third category, modifications to general relativity, is the most radical and the most theoretically hazardous. General relativity has passed every experimental test to which it has been subjected with extraordinary precision, from the perihelion precession of Mercury to the deflection of starlight around the Sun, to the gravitational wave signals detected by LIGO and Virgo from merging black holes and neutron stars. Proposing a modification to general relativity that would affect the Hubble tension while not disturbing any of these existing tests requires extraordinary care. One category of modified gravity theories, called scalar tensor theories, introduces a new scalar field that couples to gravity in a way that effectively makes the gravitational constant g different from its local tested value on cosmological scales, if g were slightly different in the early universe. Either because of a running coupling or because of a new field, the expansion rate in that era would be affected and the sound horizon would shift. Some scalar tensor theories make this prediction with controlled approximations that avoid conflicting with local tests of gravity, but none have yet been shown to simultaneously resolve the Hubble tension, preserve the baryon acoustic oscillation fits, and not conflict with gravitational wave propagation speeds. A constraint imposed by the observation of gravitational waves from the neutron star merger GW17081 seen in 2017, which arrived at essentially the same time as the electromagnetic counterpart, constraining the gravitational wave speed to within 1 part in 10/4 of the speed of light. One candidate beyond standard solution deserves special attention for its conceptual elegance and its compatibility with multiple cosmological observations, interacting dark energy, in which dark energy and dark matter exchange energy or momentum through some coupling beyond simple gravitational interaction. In a universe where dark energy decays into dark matter over time, the dark energy density would decrease while the dark matter density increases, precisely the direction that the DESI data appears to indicate. More intriguingly, such an interaction could potentially reconcile both the Hubble tension and the S-Tray tension simultaneously, because the late-time redistribution of energy between dark components would alter both the expansion history and the growth rate of cosmic structure. But the observational constraints on such interactions are tight, and the theoretical motivation, the identity of the coupling between two substances we don't understand, remains poorly grounded. There is one independent observational probe of the Hubble constant that has not yet been discussed, and which could, in principle, arbitrate between the competing measurements without relying on any of the disputed distance ladder techniques. It is called the Standard Siren Method. In September 2017, the LIGO and Virgo gravitational wave detectors recorded a signal from the inspiral and merger of 2 neutron stars, an event designated GW17081, located in the galaxy NGC 4993, approximately 40 megaparsecs away. Gravitational waves are ripples in space-time, and their amplitude depends on the intrinsic energy of the merger and the distance to the source. From the gravitational wave signal alone, the distance to the merger can be inferred. No distance ladder, no standard candle, no calibration chain, just the physics of general relativity applied to the waveform. The recession velocity of the host galaxy NGC 4993 was measured independently from its redshift, and combining distance and recession velocity gives H0 directly and independently. The 2017 measurement yielded H070, 0 plus 12 km per second per megaparsec, a number sitting between the two camps, with an uncertainty far too large to arbitrate between them. But the method is real, it is independent, and it will improve. LIGO's sensitivity improves with each observing run, expanding the volume of the universe in which neutron star mergers can be detected. As more events accumulate, and as the method is extended to dark sirens, gravitational wave events without electromagnetic counterparts, whose host galaxies are identified statistically, the standard siren measurement of H0 will tighten. Current estimates project that with approximately 50 well-localized binary neutron star mergers, the standard siren H0 could reach a precision of a few percent, enough to meaningfully discriminate between 67.4 and 73.04. The Laser Interferometer Space Antenna, LISA, a space-based gravitational wave detector approved by the European Space Agency for launch in the mid-2030s, will detect supermassive black hole binary mergers across cosmic history, events so loud in gravitational waves that their distance can be measured to extraordinary precision, even at redshifts where individual Cepheids cannot be resolved. LISA's H0 measurement could achieve sub-percent precision, finally providing the independent arbitration that the Hubble tension requires. I find it genuinely haunting that the resolution to the deepest crisis in modern cosmology may depend on listening to the sound of two dead stars colliding, billions of light years away, through detectors capable of measuring a displacement smaller than 1,000th of the diameter of a proton. But that is where we are, and it is, in its way, magnificent. The other major new observational front is the Euclid Space Telescope, launched in July 2023 by the European Space Agency. Euclid is a wide-field optical and near-infrared telescope designed to map the large-scale structure of the universe across 15 zeros and square degrees of sky, roughly 1/3 of the entire sky, out to redshifts of approximately 2, covering the last 10 billion years of cosmic history. Euclid's primary science goals include measuring the baryon acoustic oscillation signal and weak gravitational lensing at unprecedented precision, both of which will constrain H0 and the dark energy equation of state. Its first full data release is expected in the mid-2020s. The Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, is a 10-year imaging survey that will photograph the entire southern sky every 3 to 4 nights, discovering and characterizing millions of Type Ia supernovae across a broader range of redshifts than any previous survey. The LSST dataset will be the largest astronomical dataset ever compiled, and its contribution to the Hubble Constant debate, through the largest Type Ia supernova sample in history, will be definitive in constraining late universe systematic effects in the supernova distance ladder. And then there is DESI itself, still looking. In its final year, DESI's complete dataset will contain approximately 40 to 50 million galaxies, spanning cosmic history with a resolution no prior survey has approached. If the dark energy evolution signal grows to 5 sigma or beyond, the era of the cosmological constant will be over. The community is operating in a period of extraordinary observational productivity, in which datasets that would have been considered science fiction a decade ago are now arriving on a near-annual cadence. The irony is that each new dataset has tended not to resolve the tensions, but to make them more precise. More data has meant sharper disagreements rather than convergences. This is, in the longer view of science, exactly what happens in the lead-up to a paradigm shift. The anomalies multiply, the patches fail, and then someone finds the new framework that makes the old tensions disappear, not by resolving them individually, but by showing that they were all pointing at the same missing ingredient. That missing ingredient has not yet been found, but the list of things it is not has grown considerably. And in science, knowing what something is not is often most of the work of discovering what it is. We stand, in the mid-2020s, in the most scientifically consequential period in the history of cosmology, a moment in which the precision of our tools has outrun the adequacy of our theories, and in which the universe is, for the first time since the 1990s, telling us something genuinely new. The question is not whether the lambda CDM model is under pressure. It is. The question is what replaces it, and that answer, when it comes, will reshape not only our understanding of the cosmos, but the practical frontiers of physics, technology, and perhaps philosophy. Let us trace the possible futures. The first possibility is that the Hubble tension is resolved on the local side, that some combination of improved distance measurements, better characterized systematic errors in the Cepheid or TRGB calibrations, and the accumulation of JWST data brings the local H0 measurement down from 7304 to something closer to 70, narrowing the gap with Planck to a statistically tolerable 2 sigma. This would not fully resolve the tension, it would merely reduce it. And if the DESI dark energy evolution signal continued to strengthen independently, there would still be a problem with the standard model. But it would mean the crisis is less severe on the expansion rate front specifically, and that the priority is not new physics in the early universe, but new physics in the dark energy sector. The second possibility is that the tension is resolved on the early universe side, that new CMB data from the Simons Observatory, which began operations in Chile in 2023, and is designed to measure the small-scale CMB power spectrum with unprecedented precision, finds evidence of an additional component, extra dark radiation, or a brief burst of early dark energy that shifts the Planck-inferred H0 upward. If the Simons Observatory data or the upcoming CMBS-4 experiment, a next-generation ground-based observatory that will eventually deploy across both hemispheres with thousands of detectors, measures a value of NEF that is significantly higher than 3.044, or if it finds a feature in the CMB power spectrum that is the signature of a scalar field active before recombination, then the theoretical community will have a specific target for model building. The constraints will narrow dramatically. The physics will become real rather than speculative. The third possibility, the most disruptive, the most intellectually thrilling, and the one that keeps the most theorists awake at night, is that the standard model is wrong in a deep way that no patch can fix, that the 6-parameter lambda CDM framework, despite its extraordinary successes, is operating well outside its domain of validity, and that the Hubble tension and the dark energy evolution are not separate problems to be fixed separately, but are jointly signalling the breakdown of the theoretical framework that has housed our understanding of the cosmos since the 1990s. In this scenario, what is needed is not a patch but a successor, a new standard model of cosmology with different ingredients, different equations, different assumptions about the nature of gravity, dark matter, and dark energy that simultaneously explains everything. Lambda CDM explains and resolves the tensions it cannot. This successor does not yet exist, but there are tantalizing hints about what it might contain. One direction points toward modified gravity theories that recover general relativity on local scales, but deviate from it on cosmological scales. Theories in which the expansion of space itself is governed by equations that have a slightly different structure from those Einstein wrote down in 1915. Another direction points toward dynamical dark energy, a scalar field, a quintessence field, or a network of quantum fields, whose properties are set not by the vacuum energy of quantum field theory, but by some deeper, presently unknown mechanism. A third direction, championed by a minority but growing minority of cosmologists, points toward a fundamental reconsideration of what dark matter is and how it interacts with both ordinary matter and dark energy. The stakes of getting this right are not merely academic. The fate of the universe, in the most literal physical sense, depends on the nature of dark energy. If dark energy is a cosmological constant, then the universe expands forever, accelerating at a rate that eventually pulls every galaxy beyond the observational horizon of every other, leaving each island of matter isolated in a vast, cold, ever-cooling void. In this heat death, galaxies, then stars, then planets will run down and go dark. The universe's last light will extinguish perhaps 10 to the power of 14 years from now. 100 trillion years of stellar burning, followed by the slow evaporation of black holes through Hawking radiation over timescales of 10 to the power of 67 years and beyond, followed by an infinite cold darkness. If dark energy is weakening, if the DESI signal is real and strengthening, then this fate is not certain. A dark energy that continues to weaken might eventually hand the universe back to gravity. The expansion might decelerate. Over incomprehensible timescales, the cosmos might reconverge, approaching the inverse of the Big Bang. A big crunch, a return to the infinitely hot and dense conditions of the beginning. Whether such a crunch would give rise to a new bang, whether the universe might be cyclic, bouncing from one hot state to another, is a question that depends on quantum gravity, a theory we do not yet have. If dark energy crosses the phantom boundary, if the DESI data's early cosmic history signature of phantom behaviour is real and not a systematic artifact, then the acceleration would increase. The universe would not merely expand forever, but expand with increasing ferocity. Galaxy clusters would be torn apart perhaps 60 billion years from now, then individual galaxies 100 billion years from now, then stellar systems, then planets, then atoms. The Big Rip remains a possibility that the data does not currently require but cannot yet exclude. The question of which fate awaits the universe is at this moment genuinely open. That openness is not ignorance. It is science at its most honest. There is a different kind of consequence that is both closer in time and more personally confronting. The resolution of the Hubble tension is likely to require either new fundamental particles, new fundamental forces, or a fundamental modification of gravity. Any of these would represent a discovery comparable in its theoretical implications to the detection of the Higgs boson in 2012, or larger. The Higgs completed the standard model of particle physics. Whatever resolves the Hubble tension will likely point beyond it. Consider what early dark energy implies, if it is correct. A scalar field, decaying in the early universe, contributing a few % of the total energy density at recombination. This is not a tiny perturbation. This is a new ingredient, a new particle, a new field that existed in the universe at the highest energies ever studied cosmologically. If early dark energy is real, it would be discoverable in principle at high-energy particle colliders, or through its signatures in gravitational waves from the early universe, or through the CMB polarization patterns that would be modified by the presence of such a field during the era of inflation. It would open a new window into the particle physics of the very early universe that is completely inaccessible through any other means. Consider what the DESI dark energy evolution implies, if it is correct. The energy of the vacuum is not constant. The field that drives cosmic acceleration is dynamical. It changes, evolves, possibly decays. This has implications not only for the fate of the universe, but for the foundations of quantum field theory. The cosmological constant problem, that 10 queried for discrepancy between theoretical prediction and observation, would take on a new character. Perhaps the vacuum energy is not what drives acceleration at all. Perhaps the problem has been asking the wrong question. A dynamical dark energy field, properly understood, might dissolve the cosmological constant problem by rendering it irrelevant, by showing that the relevant quantity is not the vacuum energy, but the properties of a field that is not the vacuum, and whose energy scale is set by some physics beyond the standard model at a completely different and much more tractable energy scale. And consider what a modification to gravity would imply if the universe's expansion on cosmological scales is governed not by Einstein's general relativity, but by some extension or modification of it, whether scalar tensor gravity, massive gravity, or something more exotic. Then every cosmological measurement made under the assumption of general relativity would need to be reinterpreted. The distances we infer from supernovae, the structure we observe in galaxy surveys, the primordial parameters we extract from the CMB, All of these are theory-dependent in ways that are sometimes obscured by the formalism. A new theory of gravity would not merely change the numbers, it would change the meaning of the numbers, and that reinterpretation would take decades. The next generation of experiments, Euclid, DESI Year 5, the Simons Observatory, CMBS-4, the Vera Rubin Observatory, LISA, will collectively provide, by the early 2030s, a dataset that should be able to distinguish between all of the currently viable solutions to the Hubble tension at high confidence. Either the tension will narrow, pointing to systematic errors in one of the distance measurements, or it will persist and sharpen, demanding new physics at levels of confidence that no serious scientist can dismiss. The community knows this. They are building toward a verdict. In the meantime, the universe continues to expand. Every second, the galaxies beyond our local group recede a little further. The photons from the earliest moments of time continue to cool, growing longer in wavelength, fainter in energy, approaching the silence of absolute zero over timescales that dwarf the age of everything. We are living in the briefest imaginable moment in the life of the cosmos, an eye blink, cosmologically speaking, in which the stars still burn, in which intelligent life exists, in which instruments precise enough to detect fluctuations of 1 part in 100,000 in the temperature of 13. 8-billion-year-old light have been built and operated by the descendants of single-celled organisms that appeared on a rocky planet around an unremarkable star, that we have chosen to point those instruments at the horizon of knowledge and push beyond it, that we are not satisfied with the model, however successful, when the numbers don't quite fit, is, I think, the finest thing our species does. There is a particular quality to an open question in science that is different from ignorance. Ignorance is the absence of curiosity, the unchecked assumption that we know what we need to know. An open question is something else. It is the lit fuse of inquiry, charged with what we've already understood, pointing precisely at the boundary we haven't yet crossed. The Hubble tension is an open question of this kind. It is not a gap in the data, it is a crack in the architecture. And through that crack, for the first time in decades, a genuinely new universe might be visible. What strikes me most, having spent time with the science and the scientists at the centre of this story, is the extraordinary combination of humility and stubbornness required to work in a field like this. Wendy Friedman persisting with a middle value that pleased no one, not because she lacked the confidence to take a side, but because she trusted the physics more than the politics. Adam Rias rebuilding the distance ladder rung by rung, adding geometric anchors, adding calibration galaxies, watching the uncertainty on H0 shrink from 8% to 1.4%, and the central value refuse to move, refusing to conclude that this must be a sign of systematic error because someone else needed it to be. Seshadri Nadathur in a hotel room in Cancun, unscrambling 15 million galaxies on a December night in 2024, staring at a plot that rewrote the energy content of the universe, and calling it the best moment of his career. Science, at this level, is deeply personal. These are not objective functions being minimized by emotionless machines. These are human beings, with careers and commitments and reputations, and the specific intractable stubbornness of people who have looked at the universe long enough to feel its weight. Every measurement in this story is the result of 100 quiet acts of care, checking the analysis, cleaning the data, questioning the assumption, running the code again at 2 a.m. because something in the residuals looked slightly wrong. The precision that makes the Hubble tension disturbing, the fact that the two camps disagree by 2% rather than by a factor of 2, is the result of decades of accumulated craft. The tension is only legible because the measurements are good, which means the tension is a tribute to the people who made them. They have handed the cosmos back to us with a question mark of extraordinary specificity. Here is the universe. Now explain this. Here is what I find genuinely moving about the moment we are in. We built the Hubble Space Telescope to measure the Hubble Constant. We built it to end a decades-long argument between two groups of astronomers who disagreed by a factor of 2. It did that. And then it handed us a new argument, not between two groups of astronomers, but between two epochs of cosmic history, between the young universe and the old universe, between what the cosmos was and what the cosmos is. The same instrument that answered one generation's question has authored the next generation's crisis. That recursion, that pattern of every answer containing a sharper question, is the deepest truth about the scientific enterprise. We do not make progress by arriving. We make progress by discovering that we are further from arrival than we thought. Einstein thought the universe was static. It wasn't. Hubble thought the expansion rate was 500. It wasn't. The Standard Model thought dark energy was constant. It may not be. Each correction is a gift. Uncomfortable, disorienting, productive. Each correction is the universe telling us, with characteristic impersonality, that it is more complex than our best previous approximation. It has never stopped doing this. There is no reason to expect it will. The universe is expanding, but it is expanding in a way that makes no sense given everything we currently know. And I find that the most remarkable sentence in all of science right now, not because it announces failure, but because it announces the next stage of understanding. The not making sense is precisely where we need to look. The not making sense is the leading edge of the territory beyond the map. Somewhere in the coming decade, in the data from a dark siren gravitational wave event, in a sub% detection of Neff deviation from the Simons Observatory, in a galaxy survey that resolves the baryon acoustic oscillations at redshift 2 with a precision that distinguishes quintessence from vacuum energy, the next piece will fall. Someone will look at a plot and feel that particular sensation that scientists describe with varying degrees of embarrassment but uniform recognition. The feeling that something very old and very large just got a little clearer. The Hubble tension might not be resolved, but it will be understood differently, and understanding it differently will be a form of answer, not to the question of how fast the universe is expanding, but to the deeper question of what kind of universe we are living in. That question, perhaps, does not need an answer. It needs the asking. It needs the satellites and the robotic telescopes, and the cryogenic detectors, and the hotel rooms in Cancun, and the years of patient, careful, occasionally wrong, but always earnest human effort. It needs the next generation of scientists who will look at the plots from Euclid and Rubin and Lisa and find the thing we didn't expect to find, the thing no current model predicts, the thing that makes them put the paper down and sit with it for a moment, in something that has no word in science, but has a name in the older, quieter traditions of human inquiry: wonder. The universe is approximately 93 billion light-years across. It contains somewhere between 200 billion and 2 trillion galaxies. Each galaxy contains billions of stars. Each star in its nucleosynthetic furnace has been forging the elements from which planets and people are made. And in this particular corner of this particular galaxy, at this particular eye blink of cosmic time, a species that has been literate for 5,000 years out of a 13.8 billion year cosmic history, is looking back at the light of the beginning and finding, at the precision of 1 part in 100, that the universe doesn't quite add up, and instead of rounding the number, they are asking why. That is who we are, that is what we do, and the answer, when it comes, belongs to whoever looks next.